Okay, so very warm welcome, everyone. Today, our project seminar series, we lost Dr. Emily Adlam. It's a big pleasure to have her in our seminar. And she's a postdoc at the Rutman Institute, the University of Western Ontario, Canada. And she shall present today a talk devoted to one of the central topics of our project, and is entitled, "Is there causation in fundamental physics? A relic of bygone age, surviving like the monarchy only because it's wrong, supposed to do no harm." Welcome, Emily. In reality, your subtitle of this talk was New Insights from Process, Matrices, and Quantum Causal Modeling. So we're very much happy to have you here, and I'll leave it to you.
Great. Thank you very much. Thank you for the invitation. It's great to be here. Yeah, so the question I want to address today is this age-old question: is there causation in fundamental physics? As you may know, more than 100 years ago now, Bertrand Russell very famously claimed that there is no causation in science. And he, as he scathingly put it, causation is a relic of a bygone age, surviving like the monarchy, only because it is erroneously supposed to do no harm. Now, Russell's conclusion has been moderated somewhat since that time. It's now reasonably well acknowledged that causation is certainly important in science when we are dealing with the macroscopic world, because it's useful to understand the possibilities for us to intervene on things and create desired effects. But nonetheless, many people continue to believe that there is no causation inside of fundamental physics itself. Causation is something which arises at the macroscopic level due to something like the thermodynamic gradient. So in light of that sort of quite widespread consensus, it might seem quite surprising that of recent years, we've seen the emergence of a number of research programs in quantum foundations aiming to study causation. So I'm referring in particular to the process matrix formalism and to quantum causal modeling, both of which seem to be concerned with causation in quantum physics. So the more specific question I want to address today is, what is going on here? Are these research programs counterexamples to the idea that there is no causation in fundamental physics? Or are they perhaps using the word causation in a different way to how philosophers and people in their everyday lives tend to use the word causation? So I'm going to begin by giving an overview of both the process matrix research program and the causal modeling research program. I'm then going to talk about an experiment called the quantum switch, which I think is a really useful way to show up the differences in the way in which the term causation is being used in these two research programs. I'll use that to motivate the definition of something I refer to as causal order, which I argue is what is really being studied in the process matrix formalism. And I will argue that causal order, unlike ordinary causation, doesn't necessarily involve any asymmetry. I'll also suggest that causal order is an important part of the story that we have to tell about the origins of causation in a more ordinary sense, and that the process matrix formalism also offers some suggestions as to the origins of causal order and thus of causal structure more generally. I'll then go back to the causal modeling research program and talk about some of the consequences of this for causal modeling, quantum causal models, and other non-classical causal models. So to begin with, the idea of the process matrix formalism is to try to study processes which can be implemented using classical or quantum physics without the assumption of a fixed space-time background. So we imagine processes being carried out with operations taking place in various separate laboratories and a process connecting them, but there's no requirement that these laboratories stand in any well-defined causal or temporal order. They can be implemented in loops and things like that. So the obvious problem with implementing processes like this without a fixed temporal or causal background is that you can end up with contradictions. So consider the example shown here. So my past self, Emily 1, takes the value of some bit and sends that via some process as a message to my future self, Emily 2. Emily 2 receives that bit and then performs a bit flip operation. So now the bit has a different value. And then Emily 2 sends it backwards around using another process such that it arrives at my past self, Emily 1, just in time for her to use it as the content of her original message. So what we seem to have here is a bit which has two different values at the same time. We have both the original value and the flipped value are the value of that bit at one and the same time. And that looks like a contradiction. So it seems as though if we're going to implement processes without a fixed space-time or temporal background, we're going to need to do something to prevent contradictions of this kind from arising. And there are basically two ways you could envision doing that. One would be to say there are sort of some global constraints which determine what kinds of compositions of processes can be performed. So in particular, in this example, it must just be impossible for Emily to perform this bit flip operation. That's just not a possible composition. The alternative is to say that all compositions which appear to be possible according to our understanding of local physics are indeed possible, but we're instead going to place restrictions on the set of all processes such that there just are no available processes which could possibly lead to contradictions. So in this example, that would mean that Emily too can indeed perform this bit flip, which is just a local operation which is allowed by classical and quantum physics. But the overall process in which the value of some bit is sent round in a circle from Emily 2 and back to Emily 2 is just not possible. That is not a process which is allowed to be implemented. So that is the route that the process matrix formalism takes. They say we're going to assume that agents can locally perform whatever operations and compositions of processes are permitted by classical physics, and we're going to determine a set of processes which is compatible with that, such that even though there is no fixed temporal background, they will never give rise to contradictions like this. So basically, the classical version of that encodes all dynamics which are compatible with agents locally being able to perform any allowed classical operations, but which won't give contradictions. And the quantum version is just the same thing, but the agents are now able to perform quantum operations, and we have quantum processes. So that mathematically, that is all encoded in a process matrix, which is a higher order map from a set of quantum operations to another operation. So the idea is that you put into the process matrix the set of all the operations that are performed by agents locally in their individual laboratories, and the process matrix formalism then tells you what the net effect of performing those operations will be in the context of this process. And we can put mathematical conditions on the process matrix which guarantee that no matter what operations the agents perform locally, no contradictions will ever ensue. And within that framework, we can define a hierarchy of different processes with different causal properties. So we can have causally ordered processes, which are sort of the most familiar type of processes. Those are compatible with the existence of a strict partial order, such that the outcomes in some laboratory depend only on settings in laboratories which are earlier in that order. So in real life, that order would typically correspond to temporal order. But in the process matrix formalism, we're not assuming the existence of background temporal order. So that order is just a property of the process itself. Similarly, we can have causally separable process matrices. Those are the ones that can be written as a probabilistic decomposition of processes which are causally ordered in the familiar sense. And then we can also have matrices which are causal, which means that in some cases, we allow the order of parts of the process which are later to depend on the outcomes of experiments earlier in the process. So the order is then a bit more dynamical, and it can change between different experiments, but nonetheless, we still have overall a well-defined strict partial order for each individual experiment. So all of those types of processes can be and have been implemented in the real world. We can also define some non-causal processes which currently haven't been implemented in reality, and we don't know how to implement them in reality, but they are still viable process matrices and they don't lead to contradictions. So that includes things like processes implemented on closed loops or closed time-like curves. Clearly, a process which forms a loop can't be assigned a simple, well-defined order in the way that causal processes can, but nonetheless, we can still define such processes in such a way that they will never produce contradictions. So next, I want to turn to the causal modeling research program. The causal modeling research program was inspired by research by people like Judea Pearl on how to represent causal relationships in the ordinary macroscopic world. So the idea is that causal relationships should be represented by a directed acyclic graph with obeying certain mathematical conditions. And we can use mathematical tools to infer things about the causal structure of a set of events based on our understanding of the underlying directed acyclic graph. So recently it has become popular to apply this methodology also to quantum mechanics. So for example, one important result of that research program is due to Wood and Speckens, who showed that any classical causal model which reproduces the Bell correlations must be fine-tuned in the specific sense that the underlying causal model must postulate some causal connections between the two experiments and the two measurements in that Bell experiment. But of course, those events appear causally unconnected at the level of the empirical statistics because we have no signaling. And so there is a situation where there are causal connections in the underlying model, which just mysteriously don't appear in the empirical statistics. There's also a quantum generalization of this. So instead of trying to assign a classical causal structure to quantum mechanics, one can instead try to assign a quantum causal structure to quantum mechanics. And so that involves transforming the classical nodes into quantum nodes defined by Hilbert spaces and allowing the operations to have a quantum form. So again, in that case, we end up with a process operator mapping operations to net effect. So that is quite similar to what we saw in the process matrix formalism. So having introduced those two research programs, I now want to look a little bit more closely at the differences between the notion of causation that they are using. So it's helpful to do that by considering a specific experiment, which was originally proposed in the process matrix formalism, and which has led to some debate between proponents of process matrices and proponents of causal modeling. So the quantum switch is really a very simple experiment. It simply involves using a control qubit to determine the order in which two quantum gates A and B are applied to some quantum system. What that means, of course, is that if we prepare our control qubit in a superposition of two states, we will then end up with a quantum circuit which involves a superposition of two different orders. In one branch, we will have gate A applied and then gate B applied, and then in the other branch, we will have gate B applied and then gate A applied. So the proponents of the process matrix formalism argue that what we have here is indefinite causal structure. There's a superposition of two kind of different causal structures in this situation. On the other hand, proponents of the causal modeling program have questioned that way of thinking about this experiment. And so McLean et al. In particular have a number of objections to that idea. One objection they make is that it's unclear that we should really think of those two branches as containing the same events in a different order. They suggest that we should just think of them as containing distinct copies of these events or distinct copies of the gates. However, it's been shown by Kirabella and Christiansen that in fact the circuit that is constructed in the quantum switch experiment is not in fact equivalent to the superposition of two different copies of the gates. Its effect is equivalent to the superposition of a qubit traveling to a single copy of those gates in different orders. So when we look at the actual effect of this circuit, what actually goes on appears to support the conclusion that indeed what we have here is really the same events in two different orders rather than different copies of gates in different branches. So in that sense, it does seem to be correct to say that we really do have a superposition of two different orders in this experiment. McLean and al. Also object that even if we do have the same event in each branches, nonetheless we don't have a superposition of different causal structures because the causal structure is the same in both branches. So specifically, they want to say that in both branches, the control qubit is the cause of both A and B. So even if A comes before B, in this particular scenario, A is not the cause of B, and vice versa. If B comes before A, B is not the cause of A. In fact, both of them are being caused by the application of the control qubit, which is what causes the gates to be applied. And this, I think, is indeed a correct description of the causal structure of this experiment, if by causal structure what you mean is ordinary asymmetric cause-effect relations. It is true that the gates are not causing each other to be applied. But I also think that the process matrix formalism never really meant to suggest that what we had in this experiment was a superposition of two causal structures in that sort of asymmetric sense. Rather, what they wanted to say is that we have a superposition of different causal orders, and causal orders, it seems, is not the same thing as causal cause-effect relations in the ordinary everyday sense. So what exactly is causal order if it is not just our ordinary conception of cause-effect relations? Well, it's not sort of explicitly stated in the process matrix formalism what they mean by causal order, but this is my best attempt at providing a definition of what causal order means in this context. So basically, we take some subset of the laboratories in the process and we condition on a fixed order for the other laboratories. So we're just looking at some subset now. And we can say that there is causal order present in that subset, provided that first, there exists at least one choice of strict partial order for that subset, which is compatible with the signal requirement. And second, there is at least one choice of strict partial order for the laboratories, which is not compatible with the signal requirement. So here, the signal requirement refers to the condition we looked at earlier. It's the idea that the results obtained in some laboratory should depend only on the inputs in that laboratory and on earlier events according to the chosen order. So the requirement is that the order should kind of only allow signaling forwards in the order and not backwards in the order. And the idea is that imposing this requirement on processes in some cases kind of imposes a natural order, because there will be some orders that we can choose for the process which are compatible with this idea and others that are not. So by imposing the signal requirement, we see that there is kind of an inherent order in the definition of the process itself. Now, it may be tempting to elide causal order with temporal order, because in most sort of real life situations, the causal order, of course, coincides with the temporal order. But we should avoid making that identification because, of course, the point of the process matrix formalism is precisely to understand processes in the absence of a background temporal order. And therefore, the causal order can't just be temporal order. Rather, it is a type of order which comes from the definition of the process itself, regardless of how the process is embedded in space-time. So it's important for us later to recognize that there are two different ways that a process can fail to exhibit causal order. So one possibility is that there is no order for it which is compatible with the signal requirement. In particular, that occurs for processes which are non-causals. We saw earlier that there are some non-causal processes, but yeah, not now. There are some non-causal processes which have the property that there is no possible way of putting them in an order which satisfies the signal requirement, and therefore those processes can't exhibit any causal order. The alternative is that a process may fail to exhibit causal order because all possible orders for it are compatible with the signal requirement. So in particular, that tends to happen with processes which don't allow signaling between their laboratories, because if no laboratories can signal to each other, then you will trivially always have it that laboratories depend only on inputs in their own laboratory or earlier ones, because they can't depend on other laboratories at all. So in general, processes which are non-signaling will not exhibit causal order. Finally, note that the term causal in the definitions, causally ordered, causally separable, and causal as used in the process matrix formalism, are clearly referring to something like this and not to cause effect in the ordinary everyday sense. So that supports the conclusion that the process matrix formalism is really studying this kind of concept of causal order and not cause effect in the ordinary everyday sense. So the process matrix formalism indicates to us that there is some concept of causal order which can potentially be inherent in fundamental physics itself, because, as we saw, a causal order arises purely out of the definition of the process and not out of extraneous factors like how we're intervening on it or how it is implemented in space-time. So is the presence of causal order in fundamental physics a counterexample to Russell's claim that there is no causation in fundamental physics? Well, it's helpful, I think, to take a more detailed look at the nature of the arguments that Russell gave for the conclusion that there is no causation in fundamental physics. In particular, perhaps his most enduring argument was that causation in the ordinary sense is supposed to be asymmetric. The cause causes its effect and not vice versa. And as Frisch notes, the idea that causation is asymmetric is in some sense kind of the core of the notion of how we think about causation in the macroscopic world. And the important point to observe here is that causal order does not in fact require any asymmetry. To see that, it's helpful to make a distinction between directedness and order. So for example, consider a ladder which is symmetric about its horizontal axis. That ladder isn't asymmetric. It's not intrinsically ordered in any way or directed. There's no objective fact of the matter about which end of the ladder is the top and which end is the bottom. But nonetheless, that ladder does instantiate a well-defined order. If you start at one end and go towards the other end, you will find that the rungs appear in some well-defined order. If you start at the other end, you will also find a well-defined order, which is just the reverse of the previous order. So a ladder is an example of a case where we have well-defined order without asymmetry or directedness. To formalize that idea, I use the term by order to refer to the equivalence class consisting of an ordinary directed order and the corresponding directed order obtained by simply reversing the direction of all the relations making up the order. So a by order kind of refers to as an object where we are interested in the structure of the order, but we are not interested in the particular direction of the arrows in the graph representing the order. And so going back to causal order, it's quite straightforward to see that causal order really requires only a by order and not a direction or an asymmetry. To see that, note that if you take some process which instantiates causal order and then you time reverse that process, by which I mean turn all the inputs into outputs and vice versa, in many cases what you will get is another process which also instantiates causal order, and that causal order will just be the reverse of the previous one. You just take your original strict partial order, change the direction of all the arrows, and you will find that the process is again causally ordered in the reverse direction. So that demonstrates that a process can perfectly well exhibit causal order, even if that process is entirely time symmetric and there's no directional asymmetry in it. So basically, I conclude that, in a sense, Russell was right. There is no cause effect in the ordinary asymmetric sense in fundamental physics, but nonetheless, there is something closely related to causation in fundamental physics. It's this notion of causal order, which doesn't require any asymmetries and therefore is compatible with the fact that fundamental physics doesn't seem to have many asymmetries in it. Furthermore, I want to suggest that this notion of causal order actually plays an important role in understanding the origins of cause effect in the more ordinary sense. So I'm going to use the term strong causation to refer to our everyday notion of cause and effect and the role they play in the macroscopic world. So strong causation does have asymmetry, it does have direction, and it's the kind of thing that we typically describe by a directed acyclic graph, as in the causal modeling program. So note that if we have a causal order and a by order associated with it, if we choose a direction along that by order, we're then left with just an ordinary strict partial order. So that gives us a directed acyclic graph. It gives us exactly the kind of structure we need to make sense of causal structure in the macroscopic world. So the idea is that the underlying causal order of the microscopic world plus a direction which comes from our perspective, from the way in which we are embedded in reality and the thermodynamic facts that make up that direction. The combination of that direction with the underlying causal order is what gives rise to causal structure in the macroscopic world. So when people discuss the emergence of causation in the macroscopic world, there's a strong focus on direction. There's a lot of people who are interested in understanding where the direction comes from in this kind of story. But the importance of an underlying causal order is often not recognized or commented on. And yet it is clearly very important, because a direction on its own is not enough to give you causal structure. If you don't have underlying causal order and then you pick a direction, all you're going to get is just a big mess. So in order to get the causally ordered structure of the macroscopic world, we need not only the direction that comes from thermodynamics and from our perspective, but also the underlying causal order. So in that sense, causal order should really play a part in any account of the emergence of causation. The process matrix formalism, I think, also takes a further interesting because in addition to actually it helps explain why our world must have a causal structure. So in particular, we saw earlier that the point of the process matrix formalism is to understand what processes can be implemented if we require that processes can be arbitrarily composed, but also they should never give rise to contradictions. And a large class of process matrices, indeed all those process matrices known to be physically possible, avoid contradictions specifically because they exhibit causal order. Because if a process exhibits causal order, then it is necessarily the case that it won't give rise to contradictions because we can always put the inputs and the outputs in a well-defined order that doesn't loop back around or produce any contradictions. So it seems to me that the process matrix formalism can be understood as suggesting that assuming that the world is in some sense made up of processes which can undergo arbitrary combinations and compositions, we must have something like causal order emerging. And thus causal order can really be understood as a basic consistency condition which is required for the world to be consistent with itself. Which gives interesting insight into the origins of causation more generally in the macroscopic world, because the idea is that this consistency condition gives us causal order, and then when we choose a direction along it, we then get causal structure in the ordinary sense. Furthermore, it's also worth noting that the structure of space-time is clearly very closely related to causal order. In fact, the strict partial order associated with the causal order is in most real examples just the same as the light cone structure of space-time, which can also be described as a strict partial order. So there's also potentially a story to be told here about the origins of space-time structure. If we sort of buy the idea that processes are defined in advance of space-time, and processes and there are restrictions on processes requiring them to only have processes which can't give contradictions, it is natural for something like space-time structure to emerge from that, because we must have some kind of strict partial order coming out of the composition of these processes. So this kind of idea is still a work in progress, because there are some possible process matrices, specifically the non-causal ones, which don't exhibit causal order. So in order to kind of fully complete this story, we would also need to say something about why those non-causal process matrices don't appear. And there have been some suggestions by people working in this framework as to why that is, but this is all I think still a work in progress. But it does seem to point to some interesting possibilities for explaining why our world has to be structured the way it is. So I now want to circle back to the causal modeling research program that I discussed earlier on, and understand what these ideas about causal order mean for our attempts to use causal modeling to learn about quantum mechanics. So first off, the conclusion that there is causal order in fundamental physics goes some way towards vindicating the use of causal modeling to try to understand quantum mechanics, because we can now say more specifically that in using causal modeling, our intention is to learn about the underlying causal order that is associated with the process, with fundamental physics. And that causal order really is a feature of the physics. It's not something that we're just importing from the macroscopic world by intervening on it. So that gives us some confidence that the conclusions that we can draw by using causal modeling do tell us something real and substantive about underlying fundamental physics. However, some caution is required here, because not all parts of quantum mechanics and fundamental physics more generally will instantiate causal order. So in particular, I noted earlier that one way in which a process can fail to exhibit causal order is if that process does not have signaling between the different parts of the process. So in particular, we know that that is true of the Bell correlations. There is no signaling between the two laboratories in the Bell correlations. And straightforwardly, that means that the part of the Bell experiment pertaining to the two measurements cannot instantiate any causal order. Those measurements are not going to be ordered relative to each other as part of the process. And thus, if we accept that causal modeling in quantum mechanics is a way of finding out about the causal order in quantum mechanics, it follows that we should probably refrain from trying to use causal modeling in the classical sense to describe the Bell correlations. Those experiments do not stand in any causal order, therefore there isn't any meaningful causal structure for us to find out about in that experiment, and therefore trying to describe it in causal terms is likely to lead to misunderstandings. In particular, it's not at all surprising that we find that causal models for the Bell correlations have to be fine-tuned. they're fine-tuned because we are trying to force on those structures a causal structure on those experiments, a causal structure that they do not actually possess. And it's not surprising that that attempt leads to something which looks a bit artificial and contrived. What about the more general project of quantum causal models? So quantum causal models are somewhat different to the classical causal models because they don't stick to classical ideas about causation, but instead make it quantum. In particular, what quantum causal models essentially do is provide an operational description of quantum experiments. A quantum causal model can be understood as characterizing the minimum possible laboratory operations that you would need to produce some particular effects using quantum systems. So that they are certainly, in that sense, they are certainly very useful ways to understand the possibilities that we have for intervening on quantum systems and for using them to produce desired effects. But some people working on quantum causal models also seem inclined to draw more foundational conclusions from them. So for example, we see someone saying that quantum causal modeling will allow us to establish an account of causality in quantum theory's own terms, and that this will provide answers to many of the basic questions concerning causality in a quantum universe. Now, if those questions are just understood as referring to operational questions about how can we achieve desired effects using quantum mechanics, then I think this is correct. On the other hand, if the claim is that quantum causal models allow us to understand deep facts about the causal structure underlying causal models, I would be more cautious about that, because we have just seen that in some sense that there isn't necessarily always any causal structure underlying quantum phenomena, and just making the causal structure quantum doesn't necessarily change that situation, particularly when it's quite clear that these quantum causal models are really describing operational effects rather than describing any kind of underlying structure. So although this research program is very practically useful, I'm slightly cautious about the idea that it is giving us new insight into the fundamental nature of quantum mechanics in any sense. Now, one way to push back against that conclusion would be to adopt an approach to causation which is functional. That is an approach which says that causation just is what we use to refer to facts about how we can intervene on things and create desired effects. So taking that view essentially erases the distinction between an operational description and the description of the real causal structure, because it tells us that the real causal structure is nothing more than the operational description. And I think that is a reasonable way of defining causation. I have no particular objection to this line of argument, but what I would say is that if that is your view on causation, that simply entails that understanding the causal structure of quantum mechanics doesn't tell us anything over and beyond the facts we already knew about the operational properties of quantum mechanics. It just means that causal structure isn't really a good way of trying to understand the nature of quantum mechanics beyond any operational facts about it. So although this is a perfectly legitimate route to take, it means that you shouldn't expect to draw sort of foundational conclusions from quantum causal models. There have also been suggestions that we should be trying to come up with some other kind of non-classical causal model to describe quantum mechanics. So in particular, in this paper by Schmidt, Selby, and Spickens, they set out to find ways to disentangle the inferential or epistemic aspects of quantum mechanics from the parts which are describing the realities of nature. And their view is that the realities of nature should be a realist causal theory. They argue that realist causal theory can't be classical because of the fine-tuning issues we've already noted, but the quantum causal models also won't do because, as I said, they are largely operational and don't seem to be describing realities in any sense. So they take the view that we need to develop some new causal theory which is appropriate for describing quantum mechanics. And I think this project of trying to disentangle the epistemic and reality aspects of quantum mechanics is very important, and what they do in this paper is very interesting. But I do think I'm slightly skeptical about the idea that the correct way to describe the realities of nature must be a realist causal theory, because what we've kind of seen throughout this project is that quantum mechanics doesn't really exhibit causal structure at all in the ordinary sense. And it does sometimes exhibit something called causal order, which is related, but it doesn't even exhibit that all the time. So assuming that quantum mechanics must be described in causal terms seems to me like a bit of a mistake. It doesn't really respect the evident facts about quantum mechanics, which show that it doesn't really have a causal structure in the ordinary sense. So I would be very cautious about imposing that kind of structure on quantum mechanics, given that it doesn't seem to be inherent in the phenomena in any way. So I'll close by mentioning some possible responses that one might make to these points if one is very attached to the notion that reality should be described in causal terms. So the first would be to just insist that reality must be fundamentally causal. Many people do seem to kind of have a strong intuition that causation must be at the heart of reality, and therefore they just are inclined to assume that any meaningful description in realist terms must be causal. But I think this is not a good argument. If we've learned anything from quantum mechanics, it's that our intuitions about the way things work in the macroscopic world often don't translate very well to the microscopic world. And so we should be very cautious about assuming that just because causation is a ubiquitous feature of the macroscopic world, fundamentally the world must have a causal structure. I don't really see any good argument for that to be the case. Another response I've heard says that the whole purpose of quantum foundations is to allow us to understand quantum mechanics, and therefore we should be trying to give descriptions of quantum mechanics which retain concepts from classical physics as much as we can, because that will help us better understand quantum mechanics. So, I mean, your mileage may vary here. I personally don't buy this argument, because for me, the purpose of quantum foundations is not to just describe quantum physics in classical terms. The purpose of quantum foundations is to try to understand what is really going on with quantum mechanics. And therefore, we shouldn't be describing quantum mechanics using causal structures if we don't have any good reason to think it really has a causal structure. So I don't think that line of argument is very successful. Finally, one might take a kind of neo-Kantian approach and argue that causal concepts are just an indispensable feature of any attempt we might make to formulate an idea of reality. We're just not capable of thinking in ways that are not causal, so we're kind of stuck with describing quantum mechanics in causal terms, regardless of whether that structure is really inherent in the physics or not. This argument, I think, is just not giving us enough credit as a species. It might be a bit unfamiliar and strange to think about things in non-causal terms, but I don't think it's impossible. I think we can wrap our heads around the possibility of causal order without asymmetry and of more general structures. And I think we should certainly at least try to do so, given that there are good reasons to think that causal structure is not inherent to quantum mechanics. So to sum up, I've argued that the process matrix formalism helps us see that there is something causal in fundamental physics. There is this thing that I referred to as causal order, which is quite important to keep things, to avoid contradictions and to keep things in a sort of well-ordered structure that in the macroscopic limit gives rise to the macroscopic causal structures that we are familiar with. I've also argued that this conclusion has some consequences for the use of causal modeling in quantum mechanics. It does legitimize causal modeling in quantum mechanics to some extent, but also warns us that we should be cautious because in the parts of quantum mechanics that don't instantiate causal order, we probably shouldn't be using causal modeling. So that's about it from me. I guess we should stop and see if there are any questions.
Well, thank you very much, Emily. Thanks a lot. So now we have Q&A. I ask participants to raise their hands in case they want to ask questions. So I don't see. Oh, okay. Lorenzo Maccone.
Hi, can you hear me?
Yes.
Okay, hi. Very nice. I really enjoyed your talk. Thank you very much. There's something which you said which I'm not in full agreement, but maybe I misunderstood. So you seem to be saying that you impose consistency conditions and that is going to give a causal order. So this seems to be saying that then we will not have closed time-like curves somehow, right? Okay. So,
no, not exactly. So,
okay.
yeah, so as I said, the causal modeling, the process matrix formalism allows for some processes which are non-causal. So those are processes which can't be put in a causal order, and those processes do include some processes which can be implemented on closed time-like curves. The processes are defined such that although they are on a closed time-like curve, nonetheless, it's impossible for them to produce contradictions. So this consistency condition does also work for cases where we have closed time-like loops and loops of various kinds.
Okay, yeah, that's what I would say. So I would say that first you introduce a causal order or the space-time structure, and then on that you put consistency conditions. So I would say that that comes later, but I see you agree.
The consistency conditions come first, right? And the consistency conditions allow for a variety of solutions, many of which exhibit causal order, but there are also some solutions which don't exhibit causal order, and those are the non-causal processes. So as I said, there's still a gap in the explanation there, because we still need to understand why we don't get the non-causal processes in general. So although I think there are interesting suggestions within the process matrix formalism explaining causal order and space-time structure more generally, there is still a need to complete that by explaining why we don't see those non-causal processes most of the time.
What do you mean by non-causal? You mean like closed time-like curves which lead to contradiction, or just closed time-like curves per se?
Yeah, closed time-like curves which do not lead to contradiction. So the process matrix formalism is defined such that all processes, every valid process, will never lead to contradictions. That's mathematically built into the framework, and within that there are some processes which are on curves and others which are not on curves and which have a different order.
Okay. Thank you. Thanks.
Thank you. I have Chris and then Marco Vorgione.
I am. Can you hear me?
Yes, I can. Thank you.
Okay. Sorry, I don't have the camera won't work. Thanks for the talk. That was really, really cool. I guess I have just a doubt about MacLean reconstruction of the causal structure of the quantums, which I just probably didn't get it. So it was. Correct me if I'm wrong. So he's suggesting that we shouldn't think about like a superposition of A causing B or B causing A, but rather at the control qubit, which wouldn't be C, would be like another thing. But if I remember the quantum switch. But anyway, the idea is that whatever the input of the whole experiment is, this is going to cause the disjunctive kind of disjunctive effect. A or B, but well, I mean, I was wondering if you think of it just in counterfactual terms, in the most shallow way possible. It still is the case that if A had not happened, B wouldn't happen, given one branch, or if B hadn't happened, A wouldn't have happened in the other branch, right? So the counterfactual linking A and B are still, you know, they still seem correct, even if you grant that C causes both, right?
So I think that depends on the details of how the gates are being implemented. But if you imagine that you have the control qubit, it works in such a way that it instructs one gate to be applied, and then it instructs the next gate to be applied. I think that the correct counterfactual analysis there is that if gate A had not been applied, that would mean that the control qubit didn't instruct the first gate to be applied, but that doesn't mean the control qubit didn't instruct the second gate to be applied. So I think in that counterfactual, the correct thing to say is that if gate A hadn't been applied, then gate B would still have been applied, because gate A isn't causally connected to gate B. They just follow each other in time. Gate A isn't the cause of B. It's not. There's no mechanism by which gate A is kind of sparking off the application of gate B. They're just being separately applied one after the other.
Yeah, but I mean, sorry, I'm just trying to get it. Like, but this would just would solve the whole problem, right? Because if you don't have A causing B, but just C causing B, or the other way around, C causing A, then there wouldn't be any reason to interpret the quantum switch as a superposition of A causing B or B causing A in the first place, like Kiribello.
Yes, and I think it is wrong to interpret the quantum switch as a superposition of A causing B or B causing A. That is transparently not what is happening. Even if you throw away the superposition and you just have gate A followed by gate B, gate A is not the cause of gate B, they just follow each other in time. So that was the point I was trying to make, that this is not a superposition of A causing B or B causing A. These are not cause-effect relations in the ordinary sense, rather they are causal order. There is a meaningful difference in order in those two branches. There isn't a meaningful difference in the cause-effect relation. So there's two separate concepts we have to grasp there.
Okay, thank you. Very useful.
Okay, so Marco.
Yes, can you hear me? You should also
can.
be able to see me. Okay. Hello, thank you very much for that. So I do more have like a clarificatory question. So because I don't think I understood something. So basically you're addressing the causal order not as a partial order, but a strict partial order. And so basically you're really pushing some aspect, mainly reflexivity, I think. And then I do have a question that if you're also relinquishing kind of the time directedness of the causal relation, then I don't fully understand what would make your notion of causal order different than just a functional relation in terms of ordering on a set, for example, set theory ordering. So going forward, more like Sheldon-Smith's idea of having causation to be determined just as a functional dependence between two entities.
Yeah. So yeah, causal order is not exactly the same as the functional dependence, because causal order can be present in cases when there is no functional dependence. So the quantum switch is an example of that, because B does not depend functionally on A in any way. Those are just two gates being implemented one after another in the circuit. So there's no explicit functional dependence. It is linked to functional dependence because the importance of the causal order is that B could functionally depend on A if we replaced the gates A and B with operations which involve performing measurements and then using those measurement outcomes to determine the second gate, then you would have a functional dependence. So the causal order provides the conditions for functional dependence to be possible, but it can be present even in when you choose to perform operations such that there is no explicit functional dependence.
Oh, so you would say basically that functional dependence is a special case of some circumstance of functional.
Yeah, and so I mean the signal requirement is defined in terms of functional dependence, right? And so the kind of the conditions that are required to be that are imposed to determine causal order say that in the cases where we do operations which can show functional dependence, the functional dependence needs to be ordered in a certain way, but you still have that order present even if you choose to do different operations, and so you don't see that functional dependence.
Okay, that helped. Thank you very much.
Are there other questions? I can see Chris has already the hands.
No, it's from before. I forgot
okay.
to.
Okay.
Sorry.
So, are there other questions? Okay, I have one question, which is and let's say more related to, I would call it a superior level of analysis. So to what extent do you think that, because you mentioned this magic word in your presentation, but you didn't get, through the current debates, and so you mentioned explanation.
Yes.
So in a sense, the obsession for causality, causal order, but for causality is strictly related to explanation. So from your perspective, how do you treat the problem of explanation then? So what the use of causal order in a sense solve, but on the other leave open with respect to the basic function, I would call it, of scientific research, and which is explanation. So if you can say something more about that.
Yeah, I'm glad you asked that, because my most recent paper is about exactly this subject. So yeah, the question is, if there is no causation in fundamental physics, how can fundamental physics explain anything if you buy the idea that all meaningful scientific explanation is causal? And I think the answer to that is that we can't accept that all meaningful scientific explanation is causal, because there are regimes of reality in which don't seem to be causal, and so we shouldn't rule out the possibility that explanations can be given in those sorts of regimes. So the question for me is, how should we generalize explanation so that we can still offer explanations in those kinds of regimes? And I think there are a variety of different ways in which you could generalize explanation to do that. I'm particularly interested in explanations by constraints, which involve applying sort of principles which constrain the overall distribution of events in a sort of symmetric way. So that can take the form of things like the operational theories and generalized probabilistic theories and axiommatizations, where we apply principles, and those principles explain the overall configuration of events, but they do that without presenting the events in objective generative causal order. So yeah, this is a question I'm thinking a lot about recently, and I think it requires some changes to our conception of what scientific explanation looks like, because you can't rely on the simple idea that scientific explanation is just causal explanation if you want to explain things in regimes that don't have causal structure.
Oh, I fully agree with you in this respect. You're totally right. So are there issues, or I don't know, also clarification questions, if any? Okay, Marco.
So it's kind of related to these last questions. So would you kind of buy into, sorry, I'm waiting for my camera to turn on. Okay. Would you kind of buy into like Matthias Frisch's view on like pragmatism over causation, in the sense like, it's not like part of the fundamental structure of reality, but still it's fundamental to physics and it's pragmatic. Okay, so you would not want to say like, causation does not play any role in physics, like all Russell or followers, for example.
Yeah, causation clearly has great pragmatic importance. It's the way we describe how we can intervene on systems and produce effects. My concern is simply that we should not confuse the facts about how we can intervene on systems with features of the underlying fundamental structure, because when we intervene on fundamental physics, we are importing things like the macroscopic asymmetries into the physics, and so the conclusions we reach there are kind of a confused mix of what's really going on in fundamental physics and macroscopic facts relating to how we relate to fundamental physics. So if the aim is to understand the fundamental physics itself, we need to be careful to separate out what is really there in the physics from what is kind of a practical fact about how we are embedded in reality.
Yeah, thank you for it. It was just a curiosity, but thank you for answering that.
Okay, so are there issues? No? Okay, so we thank our speaker. And thank you very much, Emily, for your talk. And we're looking forward to seeing you in person in July in Milan for the conference, and even for other, tasks and new adventures. Thank you very much again for your talk. And thank you, everyone. And see you in the next session. Bye.
Bye-bye. Thanks.
Bye.